This is the 10th lecture in this series of this course MM 713 on aqueous corrosion and its control. In the beginning we said that we will have this course divided into two halves. The first half corresponds to the thermodynamics and kinetics of electrochemical corrosion. The second half corresponding to various forms of corrosion which are prevalent in the industries. Actually, you may call it as a form of corrosion or you may call it as a mechanisms of corrosion in broad sense. Now, this is a very practical relevance and importance for controlling corrosion, for developing new materials or to developing some design aspect of it. From all aspect of it, you need to understand the corrosion as it occurs in the industry and various components. So, broadly if you look at the Fontana book, it says about 8 forms of corrosion, but you go along you will see that that is not, there is no sanctity. You can have, you can call it as 9 forms, 10 forms or even more, because you will notice that the way you control corrosion could be different, may not be classified as 8 different ways. It can be classified as more than even 9, 10 as you see. So, the 8 forms of corrosion we still follow, but you should have an open mind to say that it is not in strict sense there are 8 forms of corrosion. Before we get into the 8 forms of corrosion, you need to broadly understand how the corrosion would occur in reality. Okay. Corrosion in reality, suppose I expose a metal to the environment and you have some environment is exposed to this, suppose there is an environment here and the corrosion occurs. What is the corrosion here? You will have an anodic reaction and you will have a cathodic reaction. Of course, the rate of anodic reaction must be equal to rate of cathodic reaction, that I think we are all well aware of it. Suppose assume that this is a metal and corrodes as let us say Mn plus n electrons, and there has to be a cathodic reaction. I generalize this cathodic reaction as some species, they accept these electrons and they get this here, and you call this is anodic and you call this as cathodic. We give some illustrations of what are the possible cathodic reactions at a later stage. Right now it is sufficient to discuss that a corrosion reaction involves anodic reaction where the electrons are released and a cathodic reaction where the electrons are accepted. Let us look at this sample here from this point of view. You can have, assume that the metal is very pure, assume that it is the best pure metal, let us say best possible pure metal, and assume that it is a single crystal, or for some reason just assume that it is a single crystal. Okay. So what will happen now? You will have an anodic reaction occurring on the surface, cathodic reaction occurring on the same surface. It will occur very randomly, right? Instantaneously you might find a place can behave as an anode, a place can behave as a cathode here. Okay. Now if this anode and the cathode, the locations are fixed, what happens? The corrosion becomes quite non-uniform. Okay, the corrosion becomes more at the anodic site, and the cathodic site the corrosion is not going to occur, and you call that as what? You call it as localized corrosion. So in localized corrosion, okay, if you look at the nature of the place like A and C, and if you look at this, and this is going to be the cathode, this is going to be the anode here, and with respect to time they almost remain as a cathode, they remain as an anode here. They are not going to change with respect to time at all, and that is what we call as a localized corrosion, right. So you will have dissolution occurring around this anode and no dissolution occurring around the cathode here. Visualize that the anode and the cathode, assume that the location A, okay, I also call this location A. Suppose I call a location 1, location 2, I just designate that as location 1 or location 2, and assume that location 1 it goes like this. This is time, this is the nature. So this is the cathode and this side becomes anode here. For some time it remains as a cathode, becomes an anode, becomes a cathode, anode and cathode, and this form of corrosion we call them as uniform corrosion. So in uniform corrosion, each location can act as a cathode and anode, and they vary with respect to time. So you lead to a reasonably, I would say, uniform corrosion all through the surface. So broadly then I would like to classify corrosion as two types: those occurring in a uniform manner all throughout the surface, and those where the anode and cathode are fixed with respect to time, they do not really change with respect to time. So they are called localized corrosion. So these are the two broad categories of corrosion that you must be having. This is very important. The way you prevent corrosion depends upon what you understand in more detail about what is localized corrosion. Of course, the uniform corrosion is fairly simple, not that complicated. Now, you will ask the question, why is that in one case the anode and the cathode sites are fixed, they are not changing? What are the factors responsible for the location on the steel surface or some metal surface where the anode becomes stable with the time, the cathode becomes stable with respect to time? Let us give an example here, okay, and see why you get into anode and cathodic site. Let us take a practical example, an engineering example where you use bimetallics. You use bimetallics sometimes, let us say you may use, let us say, steel, you may use, let us say, stainless steel, you may use. What happens in this case? In this case, the steel becomes permanently anode, the stainless steel becomes permanently cathode here. This is one type of localized corrosion, okay, and we call them as bimetallic corrosion. We also call, or we can call it as galvanic corrosions. Please notice here, the anode and cathode are macroscopic. They are quite macroscopic, they are not microscopic, right. So here the anode and cathode are macroscopic in nature. Right, is easily identifiable. I can identify this. I give another example, okay, where you have a passive metal generally that can lead to what is called as pitting or called a pitting corrosion. An example, stainless steel, in chloride medium. What is the characteristic of a stainless steel? Generally it is passivate, right. So that is a passive film on the surface. And it is possible that at some place the film damage occurs. Film damage occurs. When the film damage occurs, what happens? This becomes now an anode in this case, right. The surrounding area becomes what? The surrounding area becomes the cathode here, okay. So they become the cathode. So anode will continue to remain as an anode and the cathode will remain as cathode with respect to time, and this leads to one type of localized corrosion which is called as pitting corrosion. Please look at, this is microscopic. Is microscopic in nature, at least to start with, it may become macroscopic with time. As the pit grows, you can able to see with the magnifying glass, sometimes we can see with the naked eyes, okay. And this is another form of what is called as microscopic form of corrosion, which is called as pitting corrosion. We can have the other type of microscopic corrosion. We know that most metals in engineering applications, you do not use single crystal, do you? What kind of material that you use? It's a single crystal? You use normally polycrystalline metals, right? You use a polycrystalline metal. So what is the difference between a single crystal and a polycrystal? Grain boundaries. So generally you will have in the metals, polycrystalline metals that use okay, you will have grains, and so you have grain boundaries. They have it in polycrystalline materials. Metals and alloys, you have this. What is the difference between a grain boundary and a grain generally? What do you think? Yeah, so you have within the grain they are quite periodic, and within the grain and in the grain boundaries they are random. They are strained because the orientation of the atoms in one grain is different from the orientation of the atoms in the other grains. At the interface, it tries to optimize, tries to adjust itself, so it's strained. So the energy of the grain boundaries, what happened? So grain boundary has high energy. Right? Has high energy. So when you have high energy, what happens? That becomes now anode, and the grain becomes cathode. And you call this corrosion as intergranular corrosions. Happens. It is more complex than what I have depicted here. We will see this again in details. Okay. Now look at this, the anode and cathode are fixed with respect to time. Grain boundaries will continue to dissolve with the time, and the grains will remain as a cathode with respect to time. So you have the other form of localized corrosion. Again, please notice it is again a microscopic form of corrosion. So again it is microscopic form of localized corrosion. Now we will see the other form of corrosion, which is localized but a relatively a macroscopic form of corrosion, right? Let us look at a situation where the metals are joined, okay. One of the easy ways of joining metals is what? By riveting process, right. So you do riveting, okay. What do you do in this case? Take one piece, you take another, and use a rivet to secure that. Now you see here what you get is there is an airline gap, and the environment inside this is different from that on the outside. When I say outside means outside the this gap here, and you call this as, and this place is called as a crevice. This is also called as crevice, and so it leads to one form of corrosion called as crevice corrosion. Please look at, this is macroscopic . Is it important in industry? They are not important. Metals are joined like that, they are joined with rivets, maybe joined like your flange joints, corrosion in the flanges, in the rivet could be different. So, we need to understand the mechanism. We need to find, if you know the mechanism, you can also find remedial measures, okay. You can also try to know how to improve upon further, okay. So, we will look at the mechanism of what is called as the crevice corrosion. This is another form of localized corrosion, okay. Now, let me just go into the other form of corrosion. We use alloys. An obvious example of alloy, you know, that is copper zinc. What do you call this alloy? The brass, okay. In this alloy, you see that copper is noble and zinc is relatively active. So, what will happen now? The dissolution behavior of zinc would be different from the dissolution behavior of copper. So, you have yet another form of localized corrosion, right. This happens at what? This happens at the atomic level. They do not happen at the microscopic level, they happen at the atomic level. For example, if you take an alpha brass, it consists, let us say, somewhere between 15 to 35 weight percent of zinc, quite homogeneous, right. You really do not have too much of microstructural features except the grain boundaries. The corrosion occurs. What will happen in this case? In this case, zinc preferentially dissolves. Okay, and you call this as selective leaching, and it occurs at the atomic level. You need to find a solution, otherwise you can't use brass, you can't use this kind of brasses in seawater application, for example, you can't use them. So, you need to understand the mechanism, what is happening there, how do I improve upon the selective leaching or selective dissolution of zinc in the brass. If you remove zinc from the brass, what happens? It becomes quite porous, the strength becomes so weak, the structure cannot be holding the pressure, right, stress levels, you can't do that. So, this is another form of localized corrosion occurring at the atomic levels. So, we talked generally about problems related to the alloy, there is a grain boundaries, passive film damage, or a selective leaching we talked about, intergranular corrosion we talked about what happens in the rivet and all. There can be a situation where the environment can cause a special kind of localized attack under the flow conditions. environment. Okay. It can cause a lot of turbulence, right. So when it causes a lot of turbulence, what happens? What happens when you have turbulence? It impacts the metal surface. When impacted, what happens? There is a metal loss. So that is a mechanical damage plus a corrosion process, localized places, and you call this as it's a very interesting form of corrosion, right. It depends upon the design, it depends upon the environment, all this, it depends on the geometry of the system it goes. For example, is it a circular cross section, or is it a rectangular cross section through which the electrolyte is moving? This is other form of corrosion. This is also other form of corrosion which is called as other localized corrosions. A variation of that, we also have a cavitation damage. But these are all macroscopic. The material is not a problem, not really at fault, I would say more often. The fault, you can't say a fault, it is a requirement. You need to have high velocity in the pipeline, that is not a fault like as it is. Okay. So how do you really handle the corrosion problems in that cases? This is different. So you have flow induced corrosion, we call it, cavitation damage, we call it, erosion corrosion, we call it. There are several names given to that. We will try to understand this in detail and so that we can find a solution to the particular problem. Now, I can have a variation of what all you have seen. Suppose I have a sample, I have a structure maybe, and that I apply a stress. And it is exposed to the environment, applied stress. Okay. Applied stress. The stress can be tensile, and you can have a tensile stress. And it can be static with respect to time. Okay, and you call this leads to a failure called as stress corrosion cracking. Very prevalent in industries. I can have a stress which can be alternating stress. It can be tensile, it can be compressive, it can happen like this, or it can be tensile, and such kind of problems leads to corrosion fatigue. In stress corrosion cracking, again there can be sub classifications. You may call as hydrogen induced cracking, you may call it. Even when you have a fatigue, you can have hydrogen involved in the process. Mechanisms, they become complicated, and the solution to that problem is different from a normal stress corrosion cracking. That is why I said you can have several mechanisms, and depending upon situations, and the solution for these problems are not exactly the same. So to summarize, I would say you can broadly say that corrosion occurs in the two manner: a uniform corrosion, other is a localized corrosion. The difference between these two can be broadly again said as the uniform corrosion, the anode and the cathode locations, they keep alternating with respect to time, and so the corrosion becomes uniform. the localized corrosion, the anode and cathode, they become rigid with respect to time, and so there is going to be a localized attack. The attack can be simply a dissolution process, it can be assisted by a mechanical means such as erosion, cavitation, or it can be assisted by tensile stress or a fatigue stress can lead to cracking. So, the localized forms of corrosion are even more dangerous as compared to what is called as the uniform corrosion. So, these are broadly the classifications of that. So far, have any of you any kind of questions?
What sort of scenario decides that a metal or a part of metal will act as cathode or anode, and how do we determine the scenarios?
Yeah, see, it's an interesting question. To make a metal as anode and to make a metal as a cathode, it requires a specific properties, Momentarily at that particular location the energy has to go up, right, then that location becomes an anode and the remaining places it becomes a cathode. Assume that I have, let us say, aluminum and it is 99.9999 some 69 purity. There is no alloying elements. So, the energy of aluminum, all the aluminum atoms are same. I do not think there is much of a difference unless you associate it with dislocation or vacancies, all kind of stuffs actually, okay. So, in the absence of that, every atom in the lattice would have similar energies. So, they have equal probability of acting as a cathode and as well as an anode here. Momentarily these atoms can become an anode because after all what? After all, you see electron wave, the energies are not going to be same all the time, there can be lattice vibrations can happen, or momentarily the oxygen atom can go to the surface, can lead to that. So, the various reasons you can render the particular place as an anode and then cause dissolution. Of course, you dissolve a metal, you release electrons, the electrons have to be accepted by some other species, other places you get a cathode. So, all these variations that occur on the metal surface are mostly statistical or probabilistic issues. They are not really atomic issues. When I say atomic or deterministic means they have a character. The character of these metal all through is similar. Momentarily, stochastically they are changing and so they become anode and cathode with respect to time. You get a uniform corrosion taking place. On the other hand, you can have a compositional variation, right. Suppose you take a steel. What does steel consist of? Any of you? Typically, you see in the microscope, what do you see? You get a ferrite matrix and you may get a cementite. A cementite is of course located in the porite, right. So, you have two phases, you have ferrite phase and a cementate phase. Cementate phase is what is rich in carbon and the ferrite is very lean in the carbon content. Chemically they are different. So, you have one making as anode, other becomes a cathode. So, there can be compositional variation that can make the alloy locally anodic and cathodic can happen. It can happen in many of the alloy systems because in fact the metallurgists we develop alloys with different phases, that is why it gives you strength. Aluminum alloys, another example, you increase the strength of aluminum alloys because of what? Because by adding the elements like copper, zinc, magnesium and do heat treatment and you get the strength, but these precipitates are chemically heterogeneous. So, you can also have that is more deterministic, that is not a time bound process. So, you can have corrosion taking place along the precipitates. So, if you have to have uniform corrosion, one of the general criteria could be that you will have mostly a homogeneous alloy systems, or even you may have heterogeneous alloy systems, they are not too much biased as anode and cathode, they may be only marginally they are going to be different, so it can able to vacillate with respect to time actually. So in even normal steels, you will see generally you will get uniform corrosion. The ferrite and cementite are not going to cause so much of it, atmospheric corrosion. But you go to a laboratory and then you are going to use etchant like Pickerel or whatever you are going to use it, you can nicely reveal ferrite, you can reveal cementite because that etchant is a chemical etchant, it just etches out separately. That is essentially what is that? It is a localized corrosion. Then only you can able to see phases. So localized corrosion would depend upon differential a tendency to corrode can happen because of various reasons, okay, that we have been seeing all along like this only. So generally pure metals are more prone to uniform corrosion than pitting all kind of stuff. But then you can have a crevice corrosion, nothing to do with the metal. I can have a purely austenitic stainless steel, I can get a crevice corrosion. Why? Because it forms a crevice, external is forming there. So you need to understand from the context in which these forms of corrosion are occurring. So we will discuss also in detail what are the governing mechanism for various localized forms of corrosion. Coming back to the point here, actually, okay, if it is a very uniform metal and if the alloys generally not cold worked, grind boundaries are not too much energy difference, you will see a uniform corrosion. In fact, I used to tell people, if you take a very high pure aluminum of 99.99959 purity they call it, and then you ask to etch it, you will not get the grind boundaries revealed at all, okay. But on the other hand, you are going to have a small amount of copper, you etch it, the grind boundaries are very much revealed actually. So the purity of element is very important in seeing whether there is a uniform corrosion and localized corrosion at all. I hope I have answered the questions actually. Anybody else have any questions? Okay. So if there are no further questions, let us move on to understanding the various forms of corrosion, okay. What are the various forms of corrosion? First let us discuss the so called uniform corrosion. We have just now seen in uniform corrosion, one of the most important criteria is uniform corrosion is that the anode, the cathode, they shift with respect to the time actually here. In a symmetric manner, I did not draw a nice sinusoidal curve, okay. In a symmetric manner, you will have the location anode and cathode can take place. There are several examples. One is if you look at the rooftop, okay, of steel sheets. The steel sheets you will see around actually the uniform corrosion. Most of the atmospheric corrosion of steel structures you will see them as uniform corrosion. So you can say generally atmospheric corrosion. Steel, you see that. It could be even the steel, it could be in hydrochloric acid, it can happen in I am sorry, steel in sulfuric acid, steel in hydrochloric acid, steel in phosphoric acid, even in water generally they undergo a uniform corrosion. Okay. In all these cases you will get you might have seen pipelines around, or steel bars lying in the open atmosphere when it rains. They are all practically uniform corrosion. Some confusion however arises, I have seen when you interact with industries, they say, oh, they look like pitting. Okay. What do you mean by that? If you look at the surface is not atomistically uniform. When you say uniform, please do not mistake that it is going to be very smooth. You may have a rough surface, if you touch it you will see the roughness. That is not considered to be pitting. When you talk about pitting, we will discuss in detail what is maybe pitting, when do you call it as a pitting, all we can talk about. Okay. Shear roughness, shear within course, non-uniform corrosion is not considered as a pitting corrosion. No, it is not considered as a pitting corrosion. So that you should be able to make the distinction between what a pit is, what a rough uneven corrosion is not considered as a pitting corrosion. Now when you talk about uniform corrosion, we have seen what it is, then we have to look at what are the factors that control the uniform corrosion. First and foremost is the nature of the environment. Okay, this is one factor that you can say. The second is the temperatures. The third is the external variables like velocity. Of course, it also depends upon the alloy nature. Okay. So let us look at one after another how they affect the uniform corrosion of a metal. Let us take the nature of environment. Okay. First and foremost, I would give pH as important variation. Actually, even before that, I think it is better to talk about what are the type of anodic reactions and cathodic reactions involved in the metallic corrosion. Okay. So let's first get into the nature of anodic and cathodic reactions. Maybe it's covering there only. Let's look at this. Suppose I have a metal. So let's look at the nature of reactions. Then only you will be able to appreciate all this nature of reactions. Let's take an anodic reaction. I generalize as metal going as Mn plus Mn plus N electron. This is anodic reaction. Let us look at what are the cathodic reactions possible. Cathodic reactions are say one. It's a simple hydrogen ion reduction process and giving rise to hydrogen molecule. It can be oxygen in acidic conditions can react with H plus and electrons giving rise to possible. This is in the acidic conditions, right. You can number this cathodic reaction as 1, as 2. You can also have the oxygen here in a neutral medium. It can combine with this electron, can form, it is neutral or alkaline. Please look at it, in both cases it can happen. You can also have simple water accepting the electron, okay, simple, this is called water reduction. Right. You can have like any kind of oxidant, for you can have let us say M X plus can combine with some electrons, can become M X minus 1 plus, can happen actually, okay. This can be some oxidant. Can you give an example for this? You guys have seen already. Ferric ions, right? Ferric ions converted into ferrous ions. You can also have one more, okay. Let us say a metal ion can combine with this electron, can give rise to metal. So, it is a noble metal. I think this is an important slide for you, okay. Why it is important? Suppose you go to industry and you are given, okay, and one guy says sulfuric acid is present. We are storing sulfuric acid in a tank, so it is corroding. If you look at these equations, what do you think are relevant here in this? Look at these equations, right? Look at these equations. Tell me corrosion of stainless steels in a sulfuric acid tank, which of these reactions are relevant here? Of course, forget about the anodic reaction that is going to happen. Let us look at the cathodic reactions. What are the reactions which are relevant? Yeah, tell me. Yeah, first is relevant, the second may be relevant, then is third relevant? Is relevant third one? I won't answer, okay. Is the fourth relevant? Fifth relevant? You do not know, okay. Sixth relevant? You do not know. Now let us look at one after another. First is little obvious, sometimes it can be less obvious. If I am going to use 99.9 weight percent sulfuric acid, you might find that the first reaction itself will not be there. We will see later, because sulfuric acid cannot dissociate into H plus sulfate ions when it is highly concentrated. Timing, don't worry about it. Okay, let's assume it's a dilute sulfuric acid. Don't worry about concentrated sulfuric acid. So first question you are going to ask is that what is the concentration of the sulfuric acid? Is it concentrated, dilute? Assume it is dilute. Now the question number 1 is relevant, 2 is relevant, the third is certainly not relevant. Now the 2 is relevant or not, you have to check. Is the tank is deaerated? Is it open to atmosphere? You have to ask these questions, industry guys, I mean, how do you, the tank is not going to talk to you, right? Now the environment is going to talk to you. Now you need to apply your mind and see what happens. So we need to look at, now we need to just look at it. Now of course we can see that system is closed system, no aeration, but for sure then what happens, you may use a DO meter, dissolved oxygen meter, to say that okay, there is an oxygen content present here. The question number, the 1.5 depends upon how does the ion dissolve. If ion is dissolved and become ferric ions, it becomes relevant for you. That means you have to analyze the content of sulfuric acid. The sulfuric acid does not have ferric ions, then again I rule out the 5 is not going to be there. Okay, and the noble metal very unlikely to happen, okay, unless you have some system carried away with copper ions. So an analysis of possible corrosion processes are very important in order to diagnose the industrial problems. Okay, so you need to have a broad idea about what is likely to happen at all in this case. Okay, so these are very, very important for this. Now I ask a question to you. I have a carbon steel and I have a stainless steel. Two scenarios I am giving to you, a carbon steel and a stainless steel I am giving to you. Now you start analyzing the problem, which is beneficial, which is detrimental, what happens. Suppose a situation where the tank is open to atmosphere, where the tank is closed, no oxygen content present here. One case stainless steel, second metal is steel now. You apply this principle here, you tell me what will happen here in these cases. Let us take steel now, okay. Steel, the equation 1 is a problem. What about the equation 2, is a problem or not problem? Is a problem? No problem? Yeah, problem. Of course, the fifth is also going to be a problem. It is a aerated open. You take a stainless steel, what happens? Number 1, yeah, I won't tell, please tell me, is a problem or not a problem? It's a problem. What was number 2? Yeah, maybe a problem. Why is that maybe? Is it going to decide based on who is going to examine the problem or what? Yeah, tell me, number 2, is it a problem or no problem? You must have the answer now, because you studied already the fundamentals in the first course, first part of this course, right? Thermodynamics and kinetics you have seen. You apply this now, you tell me the 2, is it a problem for stainless steel or not a problem for stainless steel? Huh? Come on, I want to have an answer from you. Okay, I give answer for you. You defend. I hope you will defend me. Okay, I give answer for you. I say the 2 is not a problem. I say the 2 is better. Can you defend me actually? Passivity, right? So because the oxygen present in the stainless steel tank will passivate. The same oxygen present in the carbon steel tank will be harmful to you actually, the dilute disease. Okay. So you need to be trying to understand this now. What are the things? How, it's very, unless you get a comprehensive idea, you can't analyze the industrial problems. But it is very simple, you just apply the principles, okay. However complex it is, they start unraveling one after another, but you need to go in this direction. So these are all very important equations, okay. So this is how I want you to learn, is what I want you to understand this equation from the thermodynamics and a kinetics point of view, okay. So I want you to get clarity in how you approach the problems actually, okay. Now let us get into this and see how we can give solution to the people, okay. Now let me just give you an example of, let us take the equation 1, okay. The equation 1, H plus is related to pH obviously, right. So let us look at the pH now, the pH effect. If the pH is increased, what will happen to corrosion rate? What do you expect to happen of let us say steel in water, okay. What do you think will happen? Yeah, when the pH is increased, what will happen to corrosion rate? Decreasing, okay, please, and you have to be firm and clear about it. Why is when the pH is increasing the corrosion rate drops? Because H plus ions concentration is decreasing, so the corrosion rate will things. So there are certain things actually, okay, people have also had some some trend people have found, and this is the corrosion rate versus the pH. pH is going this way, is increasing reverse way actually, okay, and something like it goes actually, it is a trend actually, okay. And see, very interesting, it increases and remains stable, and then you find it is very high corrosion rate and the pH is going to be down actually here. Now you know the boiler, right. I am going to now give an example and you are going to give me a solution to the particular problem, okay. Let us take the case of boiler corrosion, fine, but does not matter, I think you guys know about boilers. What for people use boilers? Anybody? Any idea? Yeah, steam generation, right. Steam is used for many purposes. One of the purposes is to generate electricity. The second is also for heating the systems. In a chemical process industries, you use steam to heat the reactors. Right? You can't go and use electrical heaters and all, okay. They use steam to rise the temperature of a reaction process. So steam is used for two purposes. One is generating the electricity in a steam turbine, other is to heat the chemical processes involved actually. Now let us get into that. Now you please go back to the equation, and idea is to heat the steam. You are going to generate steam, steam is generated. For simplicity, I will say they use pure water. Pure water is used because you do not want to form a scale and all, people use pure water, okay. Now what is the temperature of the boiler actually? Generally, anybody has a temperature, any idea about it? What is the normal temperature of? About normally the water is heated about 250 to 300 degrees Celsius, okay. So you create this thing, okay, water is heated in the temperature range of let us say 250 to 280, something like that. They heat further to increase the efficiency of the turbine, that is not the point. The water is heated in 250 to 280 degrees Celsius depending upon the pressure of the boilers. What material do you think they use? Anybody? Material of construction? Stainless steel? You think? Nickel based alloys? Titanium alloys? Stainless steel? Somebody is saying no, you tell me what material, you know it. No, they use steels, okay, they use steels. At best they use chromoly steels. You know why they use chromoly steels? The chromium and molybdenum is not meant for corrosion resistance, they are meant for creep resistance. Please make it very clear. The chromium and moly present in this one generally are not meant for corrosion resistance. Now, if you look around, steel just exposed to atmospheric condition, water, corroding heavily, right? At that temperature, 250 degrees Celsius, 280 degrees Celsius, water, the boilers are supposed not corroding. In fact, the boiler's life is around about 30 plus, 25 plus years. Okay, some of the power plants they like to run it for 40 years. So 40 years you are supposed to use the tube, not undergoing corrosion at all, or minimal corrosion undergoing. How is that possible? The steel at that temperature not undergoing corrosion. How is that possible? Whereas the water you see around, exposed to this, you get red rust, you see here, right, flash rust. Moment rain comes, within about few hours you see a flash rust coming, right. So how is that possible here? Okay, how is that possible? You please take your notes and have a look at it and tell me how is it possible. So this is your notes, okay, right. Tell me how is it possible that the boiler can be made resistant to corrosion? Yeah, good. So you know what are the cathodic reaction, you know what are the anodic reaction. You cannot do much about anodic reaction, maybe you can do bit, we will come back to this later. First look at the cathodic reaction here. First of all, you get rid of, okay, you said deaeration. Why? Because the oxygen is one thing which is causing problem. So first thing they do is they do deaeration. The oxygen content is kept well below 1 ppb, 2 ppb, 6 ppb like of things, okay. The oxygen content is removed totally, okay. But there are different type of boilers, they keep oxygen content about 50 ppb, so let's not worry about it. But we can say that oxygen is removed completely. Then what happens? You cannot obviously keep the H plus, it's also enemy number 1. So how do you reduce this H plus? What do you do for that? Increase the pH. So you make the pH and slightly alkaline, you are going to be something like a situation 3, but remove this oxygen from here, then what happens? Now the corrosion rate of the steel significantly get reduced. How do you remove oxygen and all, let us not discuss right now, okay, that is a boiler is separate subject together, okay. But this is how the principle is. The principle is remove the species responsible for cathodic reaction, stage 1. So make the pH alkaline, remove the oxygen content, and so the corrosion rate of the boiler stops on the cathodic side. And the anodic side, what you can do? You can make the metal now passive, right. Now you have seen the Pourbaix diagram before, right. What the Pourbaix diagram is? It is a potential pH diagram. If the pH is slightly alkaline, the metal can form passive films. So you form a passive film, you remove these things, so what happens? The steel can last for 25-30 years at that temperature with the water, no corrosion problems at all actually, okay. So the basis can be applied in order to minimize the corrosion in the field actually, and it is a common practice. You go to any industry, any thermal power plant, the utility is a very important thing. The water treatment is a separate department altogether, okay. They look at, they dissolve oxygen content, they monitor the H plus content actually, means pH they monitor it, and then so the corrosion rate is now dropped. Of course the metal in that case forms a nice magnetic oxide, which means a passive oxides that also promotes the corrosion resistance of the boiler steel tubes. So that is why the basics, the fundamentals are very essential in order to solve the corrosion problems. If you go to industry, there are so many variations that happens. You, in fact, you will not see same problem faced by other industries, because after all, you have human nature, there are so many variations happening, but the basics, the fundamentals are similar all through. You can able to find a solution to the problem. Okay, you understood this one actually? Can I move further? Okay. So when it comes to boiler, these things you say that okay, this is, so that means the basics here involved, the basics involved in water treatment, pH is increased, then what happens? You also oxygen level is reduced, and both of them leads to passivation and also leads to low cathodic reaction. Now it is also important to understand corrosion in entirety. It is very difficult to know what all the different environments present in industry. There are millions of different environments. It is very difficult for you to make a tabulation of that actually. But you should be able to analyze the problem, you should be able to address the problem, okay. I will get into the other kind of environment, how the corrosion can change. Look at the case of say corrosion of steel in NaCl solution. So, if you take a steel and if I measure the corrosion rate of the steel with the addition of corrosion rate versus, if I plot, what do you think will happen to corrosion rate? Assume that let us say seawater, right, let us say take seawater, okay. Now I want to determine the corrosion rate of the steel in with a different amount of sodium chloride solution. What do you think will happen to corrosion rate? We keep adding this. We all know that seawater is very highly corrosive, right? Right. So what do you think will happen? It will keep increasing, right? So you say when you add sodium chloride more and more, the corrosion rate would increase. It is not the case, okay. If you look at the corrosion rate of that, you will see the corrosion rate like this. How do you analyze this problem? You will be able to analyze the problem only when you understand what is the anodic reaction and what is the cathodic reaction, right. What is the anodic reaction of, let us say, steel in sodium chloride solution? Yeah, come on. What is the anodic reaction here? Steel. Fe will go into Fe2 plus. Fantastic. What is the cathodic reaction here? Yeah. Why hydrogen evolution coming here? Chloride? You think this will happen? You think this Cl minus plus electron becomes Cl2 minus? Will happen? No? Do you think that this will happen? Will happen? So, sodium chloride does not actively participate in the cathodic reaction actively, does not really at all, you must understand that, okay. Neither sodium can take nor chloride can take, so won't occur. So what is the cathodic reaction here? Yeah, so you forget, so this is oxygen reaction, this is what happens, it is oxygen reaction, reduction reaction with water minus, okay, this occurs. Now you must be able to understand this clearly. If there is no chloride in the medium, only pure water, neutral water exposed to air, iron will corrode and combine with hydroxide and form what will happen? It forms ferrous hydroxide, right? Ferrous hydroxide formed on the surface will form reasonably protective, I do not say excellent. So the corrosion rate of steel in neutral water is less because it can form a loosely protective iron hydroxide, okay. That is what will happen, these two will happen. What does the chloride do? The chlorides, they damage this oxide film, so the corrosion rate is increasing because they damage the oxide film. Why does the corrosion rate decrease? Anybody with a chemistry background? When you add more and more chloride, what happens to the solubility of oxygen in water? What happened to oxygen solubility? It drops. So the oxygen solubility, if you plot the oxygen content, okay, if I plot the oxygen content, approximately if you plot like that, I am not saying exactly this is a schematic, it is not, I do not take it as the trend at all actually, the oxygen level falls down. So what happened to the overall reaction? The overall reaction will drop unless the cathodic reaction occurs, the anodic reaction will not happen. So the corrosion rate now drops actually. Now these are some examples, okay. There are several cases you see like this. The corrosion rate is dropping when you increase the environment like sodium chloride. There are several other examples, a couple of them I will give you, but you have to keep your, see, if you want to find out, you can find out because the library has got all kind of data, okay. Only thing is you have to know, oh, sulfuric acid, what happens with concentration? So nitric acid, what happened with the concentration? You have to just go and find out, then you get an answer, right. You cannot assume things. So you know very well, we have already discussed also earlier, right. We discussed already also that how the corrosion rate varies the nitric acid. Did we discuss or not? Corrosion of steel in dilute nitric acid, corrosion of steel in the concentrated nitric acid. When the concentration of nitric acid is increased significantly, what happened to corrosion rate? Yeah, this decreases, right. So it is changing. So that means you have to get a clear picture about how the environment affects corrosion. There is no linearity here, please understand. I am only trying to derive that particular point only. Do not jump into conclusions and then say the corrosion rate is decreasing or increasing, and with the concentration, temperature, all this will not happen at all. So there has to be an analysis. I come to only that particular point. You need to analyze what is happening to cathodic reaction, what is happening to anodic reaction when you change the environment actually. Both cases can change, then automatically you come to an understanding how the corrosion will change if you alter the environment at all actually. So that analysis are very, very important. Simply you do not just jump to conclusion that corrosion rate will increase and sulfuric acid concentration is increased. No, do not do that, okay. That is going to be incorrect way of analyzing things. I think there are some more issues I will tell you in the next class, and today I think we will close and we continue in the class. I think we are going to start, we are going to have a class on Saturday, right? We can do that, okay. So thank you very much. Please read this, do not read it just grossly. I think you must read it the way I am just trying to analyze the problems. Each of it you need to be reading as analysis mode, not as information mode, okay. If you do at information mode, I think you are not going to do justice to the course at all actually, okay. So that has to be done.